Hello and welcome. Today we are going to take a gentle step-by-step journey into the foundations of logic. Specifically, we are going to learn how to build, understand, and visualize what are known as compound propositions. Before we can build complex logical structures, we need our basic building blocks. In logic, our building materials are called propositions. But what exactly is a proposition? Quite simply, it is a sentence that makes a claim, and it has one strict rule. It must be definitively true or definitively false. There is no middle ground. It cannot be an opinion, it cannot be a question, and it cannot be a command. Let's look at the table to see exactly what this means. First sentence, the sky is blue. Is it a proposition? Yes, it is. It makes a claim about the world, and that claim happens to have a truth value of true. Second sentence, 2 plus 2 is 5. Now, take a moment here. Is this a proposition? Actually, yes. Even though the math is completely wrong, it is still making a definitive claim. Therefore, it is a proposition, but its truth value is simply false. Third sentence, what time is it? Is this a proposition? No, it's a question. It doesn't make sense to say, what time is it is true or false, so it has no truth value. Finally, clean your room. Again, this is a command, not a claim, so it is not a proposition and it has no truth value. Remember, to be a proposition, it just has to be a statement that we can judge as true or false. Now that we know what propositions are, let's talk about atomic propositions. Just like in chemistry, where an atom is the basic building block of matter, in logic, atomic means a statement cannot be broken down into anything smaller. An atomic proposition is a single, isolated fact. It doesn't contain connecting words like and, or not. Because writing out full sentences over and over can get tedious, logicians use something we can call the nickname rule, or variables. To save time, we give these atomic propositions a simple one-letter nickname. In computer science and math, you will almost always see the lowercase letters P, Q, and R used for this. Let's set up a scenario. Let P equal the statement, switch A is on. Let Q equal the statement, switch B is on. And let R equal the statement, the motor runs. From this point forward, whenever you see the letter P, I want your brain to instantly read the English words, switch A is on. These letters are just comfortable little placeholders for our real-world facts. So we have our basic materials, our atoms, but to build complex ideas, we need some glue to hold them together. In logic, this glue is called connectives. Here are the primary operators you need to know. Don't worry about memorizing them all at once. We will practice with them. First is negation, or the not operator. It looks like a little right-angle hook. If we write not P, it simply flips the truth value. If P was true, now it's false. Second is conjunction, or the and operator. It looks like an upward-pointing wedge. P and Q is strict. It is only true if both P and Q are true at the same time. Third is disjunction, or the or operator. It looks like a V. This one is more forgiving. P or Q is true if at least one of the variables is true. Fourth is implication, or the if-then operator. It's represented by a right-pointing arrow. This one works like a promise. The statement P implies Q is only considered false when the premise P is true, but the conclusion Q turns out to be false. In all other cases, the rule holds true. All right, let's put our atoms and our glue together. By combining these variables and connectives, we create compound propositions. Let's look at a master formula. This might look a bit intimidating at first glance, but let's read it slowly together. We have not, open parentheses, P if and only if Q, close parentheses, implies, open parentheses, P or Q, close parentheses, and R. What does this string of symbols actually mean in the real world? Let's translate it back into our machine scenario. The first part, not P if and only if Q means switch A and switch B do not have the same value. In other words, they're in different states. The arrow means then. The second part means at least one switch is on and the motor runs. So the full English translation is, if switch A and switch B are in different states, then at least one switch is on and the motor runs. See? When we break it down, a complex formula is really just a precise way of writing out a practical, real-world rule. Now that we have our rule, how do we test it to see when it's true and when it's false? The most traditional way is using a truth table. Because we have three variables, P, Q, and R, and each can be true or false, we calculate the number of rows by taking 2 to the power of 3. That gives us 8 possible scenarios, or 8 rows. Look at the table. To solve that big formula, we don't do it all at once. We work step by step, from the inside out, exactly like math class. First, we calculate our inner expression, P if and only if Q, which we call step 1. Then we negate it for step 2. Next, we calculate the other inner expression, P or Q, which is step 3. We take that result and AND it with R to get step 4. Then finally, our last operation is connecting step 2 and step 4 with our implication arrow. By creating a column for every tiny sub-expression, we keep our thoughts incredibly organized, making it almost impossible to get confused. We simply follow the logic across the row until we reach our final answer. Truth tables are fantastic, but they can be a bit flat. Sometimes it helps to literally see the shape of our logic. We can do this using syntax trees. A syntax tree shows us the exact hierarchy of our logical operations, flowing from the top down. Take a look at the diagram. At the very bottom, we have our individual atomic leaves, the P's, Q's, and R's. Moving up, you can see how the variables feed into their immediate operations, the if and only if and the or. Those results then feed upwards into the not and the and. And finally, everything leads to the very top circle, the if-then arrow. This tree perfectly represents the formula written at the bottom of the screen. It is a beautiful visual map of our logic. You might be wondering, why should I draw a tree when I already have a formula? Well, syntax trees are not just pretty pictures. They are highly practical tools. Let's look at 4 reasons why we use them. Number 1, finding the main connective. The top node, which we call the root, is always the final operation. With one glance, this tree tells you that the entire formula is fundamentally an if-then statement. Number 2, clearing up ambiguity. Syntax trees visually enforce the order of operations. You don't have to worry about counting parentheses. The branches strictly dictate what gets calculated first. Number 3, bottom-up evaluation. If you want to find a final truth value, you just plug true or false into the bottom leaves and calculate your way up the branches. We'll try this in just a moment. Number 4, computer science applications. This isn't just theory. This exact structure, known as an abstract syntax tree, or AST, is exactly how software compilers and automated systems read and execute logic behind the scenes. Let's put this tree to work and evaluate a real-world scenario from the bottom up. Let's test row 4 from our earlier truth table. In this scenario, switch A is on, so P is true, switch B is off, so Q is false, but the machine is broken, meaning the motor does not run, meaning R is false. Let's see if our overall rule holds up. Starting at the bottom left, P is true, Q is false. Because they are different, true if and only if false evaluates to false. Moving up the branch, we apply the not operation. Not false becomes true. We hold on to that. Now let's look at the bottom right. P is true, Q is false. True or false evaluates to true. Moving up, we take that true result and AND it with R, which is false. True and false evaluates to false. Finally, we arrive at the very top, the main connective. The left side gave us true, the right side gave us false. We have true implies false. Remember our rule for implications? A true premise leading to a false conclusion is the broken promise. Therefore, the final result at the top is false. Our conclusion? The overall logical rule evaluated to false. In plain English, the premise was met because the switches were in different states, but the expected conclusion failed because the motor didn't run. And that is how we build, analyze, and visualize logic. By breaking things down into atoms, understanding our connectives, and mapping them out in tables and trees, even the most complex logical puzzles become totally manageable. Thank you so much for joining me on this journey through the foundations of logic. Take a moment to celebrate what you've learned today, and I'll see you in the next lesson.